Good afternoon, everyone. My name is Brian Mark, and I'm the Dean of Science at the University of Manitoba. Before we begin today's event, I would like to acknowledge that we are located on the lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories, and we acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So I am pleased to welcome all of you to this special lecture today, entitled Dark Matter and the Expanding Universe, delivered by our esteemed guest and Faculty of Science alumnus, Dr. James Peebles. We had originally planned to host Dr. Peebles in 2020, but however, as you all know, the pandemic got in the way of all of our lives. But today, I am very delighted that Dr. Peebles, his wife Allison, members of his family, the University of Manitoba President Michael Benarosh, and you, the University of Manitoba community and friends, can join us here to celebrate Dr. Peebles' remarkable career. Dr. Peebles was born in Winnipeg and raised in St. Boniface and later in St. Vital. He began his time at the University of Manitoba studying engineering, but ultimately transferred to physics, an excellent choice, I might add. And it was during this time that he met Allison. Dr. Peebles obtained his Bachelor of Science degree in 1958 from the University of Manitoba, and then went on to Princeton University, where he obtained his PhD in 1962 under the supervision of Robert Dickey. Dr. Peebles remained at Princeton, completing his PhD to establish his own pioneering research career in physical cosmology that now underpins our core understanding of the universe today. In fact, from his theoretical contributions to cosmology, which ranges from the formation of galaxies following the Big Bang to dark matter to the accelerating expansion of the universe, multiple Nobel Prize awards have been awarded to those who have substantiated a number of his theories. Dr. Peebles is currently the Albert Einstein Professor Emeritus at Princeton University, and he received numerous awards for his brilliant work over the course of his career, including the Gold Medal of the Royal Astronomical Society in 1998, an honorary doctorate from the University of Manitoba in 1989, the Order of Manitoba in 2017, and the Nobel Prize in Physics in 2019, which recognizes his theoretical discoveries in physical cosmology. And Dr. Peebles shares this prize with Drs. Michael Mayer and Didier Queloz for their discovery of an exoplanet orbiting a solar-type star. In recognition of his extraordinary scientific achievements and his connection to Manitoba, the University of Manitoba Science and Technology Library is being renamed in his honor to the Jim Peebles Science and Technology Library. So as you can see, Jim, Manitoba is very proud of you, and it is wonderful that you and your family are able to join us today to celebrate your wonderful career. So following Dr. Peebles' lecture, which will take place in a moment, Dr. Jan English from our Faculty of Science, Physics, and Astronomy Department will moderate some questions from the audience, followed by closing remarks from the University of Manitoba President and Vice Chancellor, Dr. Michael Benarosh. There is also refreshments outside for those who are interested after the lecture. And so without further delay, please join me in welcoming Dr. Peebles to the stand. Thank you.
Thank you, Brian, for that welcome introduction. It's great to be back where I was raised. And colleagues and friends, I'm delighted to address you. My plan is to talk about aspects of what I've been doing in science for over a half a century, but I think it's well to introduce myself first by showing you a few images of how I grew up. You will see here my grandparents' home on the Peebles side. It was in St. Vital, near the Red River and near St. Mary's Road, just a few blocks this side of where it meets St. Anne's. I've looked for the remnants of the house, can't find a thing. My grandmother, Peebles, was always known to me as Minnie. My father was Andrew Charles, always known as Jim. my mother, Ada Marion, always known as Ada, then Audrey, the oldest of the children, then June, and then me, 1943, 8 years old. Well, I grew up. I have to learn how to work this thing. And there it is, 1951. I'm 16. So I went on to the University of Manitoba, where I took courses. Here is an example, mathematics, Professor Mendelssohn. I always thought he was impressive. I didn't realize just how impressive until I read his biography in Wikipedia. You might try Googling Professor Mendelssohn, Nathan Mendelssohn, mathematician. You'll read an interesting story. He had a big influence on me, but by far the big influence were the faculty and students in the physics department. I always loved to see students arguing over how to work a problem. You learn a lot from your fellow students. Of course, I also learned a lot. I meant to say, here's Professor Mendelssohn's students, or some of them. I'm there in the background. But the guy who really influenced me the most at the university is Ken Standing. You see on the left his image when he was a graduate student at Princeton University 10 years before I was a graduate student. There he is later in life. Ken somehow decided that I must go to Princeton University for graduate study. I never gave it much thought. I just said, well, if you say so, Ken. And off I went with Allison. Here she is with me. One of the great things that happened to me at this university was meeting her. She's been my best friend ever since. I went off to Princeton. Another great burst of fortunate event was I met Professor Robert Henry Dickey, always known to everyone as Bob, who had decided that the study of gravitation is just too interesting to be ignored, as it was at that time. He was a fundamental leader in showing us how to do experimental gravity physics, a subject that now has become quite rich. Beside him is David Wilkinson on the left, and me, two young members of his research group. He set our lives by saying to David and me, you might look into this notion of an expanding universe. So we did. I did it with reluctance, because at that time, the notion of an expanding universe was really very murky, very poorly supported, highly speculative. But I could see a few interesting things to do, and I did them, and that led to a few more interesting things. And so, following my nose, I set out on a career in that field. David did the same. Alas, David died too young. He should have been in on the final recognitions of the accomplishments of this subject. Anyway, I wanted to show this picture because Bob Dickey's contributions are well recognized, and one of the recognitions was a brass plaque to be put up, historic site at Princeton University, where Professor Robert Henry Dickey pioneered the field of empirical gravity physics. I lobbied hard to get the plaque put where I'm pointing, but the university resists. We can't have plaques all over the university, they said, so it's just inside the building. Well, we live with that. But I meant to say one thing. When the fateful call from the Nobel Committee came, you know, it's a tradition to call the awardees in the afternoon in Stockholm, a convenient time. So at 5 o'clock in the morning, a convenient time in Stockholm, the phone rang, I answered it. It began, are you Professor Philip James Edwin Peebles? And I said, yes. We have voted to award you the Nobel Prize in Physics. Do you accept? So I meekly said I accepted, and then the conversation grew much more friendly. But I resisted the temptation to ask him to explain why they overlooked a recognition of Bob Dickey. The Nobel Committee was well aware of my annoyance with them for that omission, but they didn't hold it against me. And I've decided, you know, it's all right. That recognition of the Nobel Prize meant a lot to me. It recognized a long career of good work, but it also recognized where I came from. Bob Dickey, Princeton University, that gave me room to grow. The University of Manitoba, that showed me what I love to do and set me off after teaching me a lot of good physics to be further trained at Princeton University. So here's a photograph of the presentation ceremony at, can I venture away from this and still be heard? I wanted to point out, if I can make this thing work. You see the orchestra, we have musical interlude. You see the king and queen of Sweden, and behind them, perhaps you can see, this thing will stop showing. I need to be on the microphone. Oh well. If you have sharp eyes, you'll be able to find me sitting next to the crown princess of Sweden, the next in line to the throne. You see Allison in red a little further over with the brother of the crown princess, and on the other side, a chemist honored with his colleagues for the invention of those remarkably effective batteries, lithium-ion batteries, that power all sorts of things these days. Maybe you've seen young people on skateboards rolling along, powered by an electric motor, powered by a small battery underneath the skateboard. Truly impressive. That is the banquet page. Oh, you're right. My one problem with not seeing what I'm talking about is I don't remember what he's talking about. Anyway, here's the king. And here's, oh yeah, it is interesting they have traditions. And one of them was I had to get up and give a toast during the banquet to be shown. These young people with caps are all students at Stockholm University, guided me up and propped me up while I gave the toast. And here is the banquet. Here, if you have excellent eyes, you'll see the queen-elect, the princess-elect and me, and further on. Can I see this? Here I am. Here's the princess-elect. Here's Allison. Here is the princess-elect brother, and here is the chemist who gave us these marvelous, efficient banquets. Here, this is a formal banquet. In which there were some 2,000 people, all dressed up, and a horde of waiters who have to be auditioned for the job, who almost instantaneously put down plates at each position. Marvelously well synchronized. We'd eat a while, we'd have a toast, we'd have a little musical interlude, and on through a happy time. Here is a photograph of the guests I had with me at the Nobel Prize. I gotta leave over. Well, you can see, you already know Audrey. Here she is. There's Audrey's old daughter, Christine. Here's our youngest daughter, Marion. Here is Leslie. And here is, you already met, Allison. So, this is good stuff. Oh, and it's nice to be back home and hear a collection of our relatives. And on to science. So we're in a galaxy of stars. It's shaped like a pancake, but the pancake has spiral arms. It looks like this galaxy nearby. We're out toward the edge. It is our home, and a home for a lot of stars, similar to this galaxy. You see patches of blue. That's where young stars have formed out of the interstellar matter. The young stars are very hot, very luminous, and very blue. You see red patches, I hope. That's where the massive stars have ionized the interstellar matter. The interstellar matter radiates a red line and shows you where they are. And you see also this thing is dying. Anyway, you see a yellowish glow, which fills the whole galaxy. That's the light of stars like the sun. There's some 10,000 million of them. The astronomers tell us that in this galaxy, and likely in our galaxy, there are about as many planets around stars as there are stars. It means that in this galaxy there's some thousands of millions of planets on which all sorts of wonderful things are happening that we can be very sure that we, the human race, will never see. It's quite a moving thought, but since this is some 10 million light years away, there's no chance we'll ever see it, and yet things are happening. It's an example of how we have a long reach, but very definitely limited. So, there are a lot of these galaxies. Here is the distribution of them across the sky. You see a tight concentration. You see a tight concentration of galaxies right near the center. That tight concentration of galaxies, a rich cluster, is in effect a galaxy of galaxies. But you see something new. Space in one part or another of this distribution looks the same. We're not seeing structure on ever larger scales as we look further and further out into space. Instead, we're seeing something else, that on large scales, the distribution of matter and radiation averages out to uniformity. That makes it possible to have a theory of the universe rather than a theory of one or more of its parts. It's because it's uniform that we can think about its mean density and its mean rate of evolution of expansion. So here is the notion of this expansion. Oh, well, first here's Albert Einstein and Willem de Sitter, a great mathematician and astronomer, at the time, I think, already director of the Leiden Observatory in the Netherlands. Willem de Sitter was one of the few people who could stand up to Einstein and tell him when he was wrong. Einstein respected that. But in fact, although de Sitter, Einstein had come to the thought that a rationally constructed universe would be the same everywhere on the large-scale average. He somehow intuited the nation of the universe as we now now know it to be. Remarkable how you can do that on occasion, but it's not something you should try at home. By and large, intuition is helpful but not guaranteed by any means. Yet in this case, Einstein somehow was right. And here is an illustration of what is meant by this uniform universe of Einstein. Imagine for the moment that we live in 2 dimensions, not 3, 2 dimensions. We live on the surface of this balloon. You can walk around the balloon, and you notice if you go in one direction, you will come back to where you were. You don't see an edge to the universe. It's the same everywhere, but yet it's finite. That's Einstein's universe from many years ago. Now it happens that Einstein soon learned it looks like this balloon is expanding. We have to be careful again. The expanding universe doesn't mean that you and I are expanding apart from the usual biological effects. Our galaxy is not expanding apart from disturbances from other galaxies, but the distances between the galaxies are increasing. And you'll notice a neat pattern. If you sit on one of these galaxies, the galaxies are represented by those little squiggles. The artist was not too inventive there. If you sit on one of these galaxies and look around, what do you see? You see the other galaxies moving away. You may say, wow, the universe is expanding away from me. But you notice that if you go to another galaxy and look around, you'll see the same thing. The universe is expanding around me. It's a wonderful, elegant arrangement that wherever you sit, you see the universe expanding, you see the galaxies moving away from you. in a pattern. The galaxies that astronomers have explored with great detail by this time, and they find that pattern indeed agrees with what is observed. Pretty good evidence that the universe is expanding. But of course, you always want cross-checks. And any daring theory, such as the notion of an evolving universe, requires a lot of evidence, and we have now a lot of evidence. So to begin with, let me remind you of thermal radiation. You've all, I expect, stood near a fireplace or a bonfire outside, held your hands close to the fire, your hands warm. That's thermal radiation. If you put a source of heat inside a container and let that radiation relax to strict equilibrium, then thermodynamics tells us the intensity of that radiation at each wavelength is determined by just one parameter. You tell me the temperature, I'll tell you the intensity at each wavelength. That's what this curve is trying to show you. Now, it turns out that our universe is filled with radiation, and we now know this is radiation with a thermal spectrum. I'll explain in a minute why I'm really excited about that. Just for the moment, let me say that checking that radiation does have this characteristic thermal spectrum was a really hard measurement. It requires bringing the detectors above the atmosphere, which gets in the way, in a satellite or rocket, and doing very careful measurements of the intensity at each wavelength. Two groups managed to do this. Others started but failed and gave up. One group in the U.S. Working with NASA, the National Aerospace and NASA. Let's call it just NASA. Here is the group, modest by modern standards. In the back, well, this pointer is not working. So the tallest guy there, John Mather, was awarded the Nobel Prize for the accomplishment of measuring this radiation and showing it looks thermal. The competitor was Herb Gush, University of British Columbia. It took them a long time. When the proposal for the NASA measurement was proposed, 15 years before the accomplishment, Herb Gush had already launched a rocket with an instrument to detect this radiation and see if it had a thermal spectrum. The measurement failed because he couldn't afford a big enough rocket to adequately shield against radiation from the Earth. But he kept working, the NASA group kept working. Oh, and I should have mentioned, Herb Gush had in his final measurements two very accomplished colleagues, Mark Halpern on the left and Ed Wishnow scratching his head. And this is a photograph of scientists at work that I dearly love. I must ask you, if you saw this image and you had no other means of judging these two people, would this image inspire confidence? But of course, they have told me, yes, I get your joke, Jim, and I've accepted it because I guess it's a compliment. But anyway, their measurement came to fruition just months after the NASA measurement. Shown here are the results of the two experiments. You don't have to pay a lot of attention to this technical graph and all that stuff. It shows that both of these experiments succeeded in showing that this radiation has relaxed to thermal equilibrium. Either one would do. The fact that there were two was certainly gratifying, a wonderful check that nothing bad had gone wrong. As I said, for the top measurement, John Mather was awarded the Nobel Prize in Physics. For the bottom measurement, Herb Gush was rewarded by the deep admiration of colleagues who know what's going on in this field. And that's it. Sometimes Canadians, you know, could be a little bit more forceful. Anyway, let's see what's next. Yeah, good. Now, I should say, and I guess I better go back, the significance of this measurement. The universe as it is now is transparent to this radiation. There is nothing that would cause this radiation to relax to this particular spectrum, this particular form, in the universe as it is now. It requires that our universe pass through a phase very different from what it is now, dense and hot enough to have relaxed to the statistical equilibrium. This is equivalent, I think, to the dinosaur footprints that show us tangible evidence that those improbable creatures actually walked the face of the earth. This is similarly close to tangible evidence that the universe passed through a state different from what it is in now. A deeply important result that should be an iconic symbol for advances in science. But of course, even that is a long way from convincing everybody that the universe has evolved from a different state. It has expanded, and as it expanded, it has cooled. For another example, at the time of this photograph, Jeff Burbidge on the left, Margaret Burbidge, his wife, also an expert astronomer, and Willie Fowler, a nuclear physicist and expert in astronomy, pictured at a conference, and meanwhile above, a review article in the 1962 on the subject, why is the universe contain so much helium? Fully a third, as later demonstrated, of the mass of the matter in our universe that is baryonic is helium. 2/3 hydrogen, traces of the heavier elements you and I are made of. Why is that? Why the great abundance of helium? It was a real puzzle, now solved, because we know that as the universe expanded through this dense state, it got hot enough to drive thermonuclear reactions that turned hydrogen into helium. That's to say, we have another piece of evidence that the universe was in a very different state, able to produce that helium. And another example. I have brought a demonstration. Maybe when you were kids, you enjoyed blowing. Isn't that neat? And you see it's a bit of elementary physics. This is shorter, so the wavelength that you generate on resonance is shorter, so it's a higher pitch, longer, lower wavelength, longer wavelength, lower pitch. And as I was just discussing with Brian Mark, it is remarkable that this simple phenomenon is observed not only here, but on the evolution of the universe in its large-scale evolution. Let's look at that. Oh, and here, another illustration of boundary conditions. A little plate of water. I nudged it slightly and took a photograph. Do you see the waves and ripples? Do you see how they align with the edge of the plate? Another example of the effect of boundary conditions on vibration. And yet another effect. The universe began very hot in this theory, so hot that electrons are stripped off ions, and so you have a sea of thermal radiation that scatters the electrons. The electrons are scattered by the ions. The result is that ions, electrons, and radiation act as a fluid with pressure. Fluids tend to oscillate. This fluid oscillates, but in time rather than space, and the oscillation is abruptly truncated when the temperature drops to about 1,000 degrees Kelvin. The electrons reattach themselves to the ions, and the matter is set free from the radiation, and the vibrations stop. That boundary condition sets characteristic patterns in the waves that are produced. These patterns are observed. Here is an illustration, but let's not get into details. Let's just look at the patterns that are formed. The bottom is the square of the Fourier transform of the galaxy distribution, if you care for those words. Never mind, though, if you don't. It is simply showing the pattern in the distribution of the galaxies, a statistical measure that in the top we see the analog for the distribution in the radiation, more complicated, but again, reliably computed. And you see the little circles, those are measurements. And you see how spectacularly well measurements agree with theory. It's even more important to my mind that these measurements in the two panels were obtained in very different ways. One, by looking at how the galaxies are distributed at fairly low distances from us. The other, the radiation that was released back when the universe expanded and cooled. The pattern then formed a long time back, measured now, and the theory agrees with both kinds of measurements. You look at the universe in two very different ways, and you get a consistent story. That's really impressive. Here I should pause to remind you of a point about natural science. And we physicists tend to be very, very proud and arrogant about our theories. For example, we say, you cannot patent a perpetual motion machine. It's not possible. We really don't mean it in quite that way. It's not a theorem. We can only say a lot of people have had a lot of experience in testing laws of physics. They constantly show us that energy is conserved. You can't have a perpetual motion machine. What's more, people have tried very hard to make them. They can't do it. That adds up to a very compelling case that a perpetual motion machine is impossible. But it's not a theorem, because our theories of physics are all incomplete. Some of them are wonderfully accurate and productive. I'll give you the example of your cell phone. Consider that scientists and engineers can make electrons and electric and magnetic fields and crystals, solid and fluid, do their bidding in operation of that cell phone. You press the button, you dial a phone number, a whole lot of spectacular physics is being exercised inside that cell phone. The physics is wonderfully well established, but yet take that same physics and push on it hard enough, it fails, because all of our physics is incomplete. That incompleteness is particularly prominent in our theory of the expanding universe. I say again, to avoid confusion, the evidence that the universe has expanded and cools seems so well cross-checked as to be convincing. But again, it's not a theorem, and certainly we can't pretend that we have the theory exactly right. The best we can argue is that it's a very good approximation, but it's easy to find in cosmology puzzles. And I turn now to one of them. Oop, did I forget to mention? Oh, again. Here is Professor Dr. Willem de Sitter again with Albert Einstein. In the early days of the idea of a relativistic universe, Einstein thought, well, it's obvious, the universe is static, it's here forever. But he ran into a problem that is illustrated in this balloon. In his theory of gravity, the general theory of relativity, the mass of the universe is going to cause that universe to collapse, as if air was leaking out of the balloon. Einstein felt that that's absurd. Surely the universe is forever. And so he modified his theory to increase it to include a term, came to be known as the cosmological constant, that had the effect of pushing material apart. And so he postulated that there is a balance, the attraction of gravity just balanced by the repulsion of the cosmological constant. He didn't recognize, this is no criticism of the truly spectacular physicist, he didn't recognize that that balance is unstable. You touch the universe a little bit, it'll either collapse or expand, unstable. Once Einstein realized the evidence that the universe is expanding, and that therefore he doesn't need this cosmological constant, his reaction was to say, away with it. That term was ugly to begin with. If it's not needed, it can't be there, surely can't be there. We see an illustration of this thinking from an exchange between Albert Einstein and the physicist in the middle, Georges Lemaitre, a Roman Catholic priest, and at the time of this photograph, the physicist who best understood the implications of Einstein's theory of general relativity. Again, no criticism to Einstein. Lemaitre understood it better. It happens. After the Second World War, you see the date 1947, Lemaitre decided that he wanted to explain to the world why he felt that Einstein's cosmological constant is not such a bad thing. He wrote to Einstein proposing to publish an article explaining why he thought the cosmological constant is interesting. Here is Einstein's response. Let me help you read it, although I have to get away a little in order to do it. I will shout, "Dear Professor Lemaitre, I thank you for your kind letter, a few kind polite words. At the bottom, it is true that the introduction of the lambda term, that's Einstein's form of lambda, offers a possibility, and it may even be that it is the right one." That was not what Einstein was thinking. We know that because later in the letter he writes, you see at the top of the full paragraph, "Since I have introduced this term, I have always a bad conscience." And at the bottom, "I cannot help to feel it strongly, and am unable to believe that such an ugly thing should be realized in nature." Here is a truly intuitive, brilliant physicist offering a very firm opinion that is dead wrong. We have learned that that wonderful fit I showed you of the result of the resonances in boundary conditions requires Einstein's cosmological constant, which causes the universe as it is now to be expanding at a rate that is increasing rather than decreasing due to the attraction of gravity. Quite astounding, but there it is. We must learn to live with lambda. I used to give colloquiums with that title, Learning to Live with Lambda, at a time when most people thought Einstein was exactly right. This term surely can't be there, but it is there. Live with it. And we come then to this question. So what does it all mean? Now, I really like, well, let's go on to the next one. I really like this couplet written by Robert Louis Stevenson. "The world is so full of a number of things, I am sure we should all be as happy as kings." This was meant, I read, to be in a child's book of verses. I looked up the comments about the verse in Google, and I found all sorts of highfalutin theories about what Louis Stevenson had in mind. I think, though, it's very simple, and it is a message that is addressed to us grown-ups as well as young children, to everyone who lives on the planet Earth. The world we see around us on scales we can observe, on scales that can be explored by microscopes, particle accelerators, telescopes, satellites, is a truly remarkable, wonderful place full of things, some of which can teach us about the nature of the world around us. Some of these things have led to the theories we have now that gives you the dubious benefit of a cell phone. I'm really unhappy to see young people in particular walking around looking at their cell phone. They should be admiring the world around us. We should all admire the world and realize that it behooves us to take better care of the place than we do. Anyway, just a parting thought then in this lecture. The world is full of a number of wonderfully interesting things. We continue to learn from them, and from them learn our place in the universe as it is. Thank you for your attention.
You're going to me a microphone. Thank you.
You should know that I've been friends with Jan for at least 20 years, is that right? Since she hosted me here on another conference.
Yes. And I can also mention that we recently met up at a conference about dark matter a few years ago, just before COVID. And there were invited guests there, about 8 of them, and they were called the gods by the rest of us, and Jim was one of them. So I'm here to moderate the questions from the audience. So there are a couple of ways you can do this. You can run up to the front and put up your hand, or you can sit in your seat and put up your hand, and someone will run over with a microphone so you can ask Jim some questions.
Sir, could you make a comment on Roger Penrose's rather outlandish theories about conformal cyclic cosmology?
Yes. First, I hope you all know Roger Penrose for his brilliant mathematics and for his prediction of black holes, for which he was awarded far later than it should have been, the Nobel Prize in Physics. Brilliant guy, and really fascinating to talk to. But you know, there are ideas and there is evidence, empirical evidence. Ideas are marvelous in research. It's wonderful to have ideas. They may be speculative, but if they lead to measurements that test ideas, they're wonderfully valuable. But in the end, you judge an idea by the evidence. In Roger's case, he is venturing out beyond where we can get any evidence. You've probably heard of other people who speculate about the multiverse, a statistical ensemble of universes. A wonderful notion too. But how in the world are you going to check it? So I'm left a little cold about such ideas. To me, the great joy of physics is to see the confrontation of theory and measurement. There is still ample room for that kind of science, and it's the kind of science that I love. I deeply respect Roger, but not necessarily his universe.
Good. Yes, right here.
Good evening, sir. Just a question for the younger generations who are interested in science. If you could give them one piece of advice, any advice on like pursuing science, what would it be?
Take an interest in the world around you. Maybe it's in the world around you very small, as in particle physics. Maybe it's the world around you on large scales, as in astronomy. Maybe it's the world around you in this immediate room. But be curious and wonder about the world as it is. A second piece of advice, of course, when you get interested in something, don't give up too easily. A real problem is to know when to fish and when to cut bait, if you know what I mean. If you have a good idea, you shouldn't let it go too easily, but you shouldn't hang on to it too long. And how do you judge? That I can't tell you.
Right here, yes. Or they saw someone other than me.
In your presentation about the expanding universe, you showed a balloon. We all know what the balloon is expanding into. What is the universe expanding into when it's the universe?
Thank you for that question. It's a very good one, and I should have remembered to caution you. Remember, I said if you live on the surface of that balloon, you mustn't ask what's off the surface. Or maybe I didn't remember to say that. You mustn't think that. Your world is the surface of the balloon. Stop. Our world is three-dimensional. you can add extra dimensions that we can never observe. That doesn't excite me. Instead, I think we should just face up to it. We're living in a three-dimensional world in which things are moving apart on large scales. You might ask, what are they moving into? And I say, you shouldn't ask that question because it's not meaningful. I don't want to be brusque, but there it is. I should avoid confusion. There is in particle physics the notion of 11-dimensional spaces. But that's on microscopic scales and not relevant to this discussion.
I'm going to ask, there's a person at the back right here, but I would like to ask you to just flesh out a bit more in the same story here. In a Scientific American article, you said, notice I said that the Big Bang was not an explosion.
Yes, would you
Okay.
disagree?
No, I agree with you, but I think that the
Okay.
media often says that it's an explosion,
Yeah.
but it goes with the surface of the balloon.
Yes, yes. So, yes, we have the phrase Big Bang, and it's stuck. So I live with it. But remember, a bang to me connotes an event at a place. There was an event, bang, and that's where it happened. Neither of those refers to our theory of the universe. Our universe in this theory is everywhere. Maybe there's an edge, but if it exists, we can't observe it. And the well-established theory describes the evolution of the universe, not an event, but evolution from very high densities to the present. So why do I allow myself to use the phrase Big Bang? Well, because if you can't beat them, join them. I'm not sure that's the right motto, but something along those lines.
Great. There's a question at the back there.
Hello. Oh, that's louder. This is a question from my 8-year-old son. He asked me this question a few weeks ago, and I didn't quite know how to answer him. What is a black hole made of? Is the matter still there, causing that singularity, or does it transform into something else?
So in the mathematical theory, a black hole began as part of the theory of general relativity. In this theory, there can be space curvature, of course, and the space curvature can be so arranged that there is a throat connecting our universe to another universe. In that case, the black hole isn't anything, it's just space curvature. There's no matter causing it to be the way it is. That's just the way the geometry works out. It's not a very good example, of course, because the theory says that black hole will soon pinch off, and then you have a singularity, and the theory prevents you from studying what happens next, according to the theory. The theory doesn't have an answer. An ordinary black hole that is made when a massive star collapses does contain somewhere in its core the mass of the star that collapsed. But it's hidden behind the throat of the black hole, no longer observable to us. So it's in there, but not observable, and for all we can tell, it may be instead a black hole connecting us to another universe.
Okay, I have 2 questions I would like. We'll have Isabel after we have this gentleman at the front here who's been patiently waiting.
And then I have a cousin sitting just in the second row.
Is that your cousin?
You're number 3.
Okay. So you, right here, yes.
Oh, I'm sorry. I didn't mean to draw you out of, I didn't mean to interrupt.
Oh, no, that's okay.
Okay, well,
So we'll just do, we have 3 more questions.
okay.
Okay, that's good. Okay, can a microphone please come over here to this gentleman with the black and white shirt?
Just basically, I'd like to know, you speak of an expanding universe. Has that always been a constant rate of expansion, or does it ebb and flow? Does it peak? Does it subside?
Good. So the theory says, and this theory is very well tested, that the expansion began very rapid And as it expanded, it slowed due to the attraction of gravity. But then that darned cosmological constant term was present, and when the density got low enough, the expansion started expanding again. The rate of expansion started increasing again. This is a terribly Baroque arrangement, and many of us wonder whether there's something deeper behind this. But in any case, the theory says, and so far the evidence agrees, that the universe has been decelerating in its expansion for a long time. Then only recently, coincidentally, as we came on the scene, as the expansion rate started to increase again.
And Isabel over here.
Did you ever expect us to discover gravitational waves or observe gravitational waves, and how do you think that will affect our understanding of astrophysics in the future as well?
So the notion of gravitational waves goes far back. When I was a graduate student, my teacher then, Bob Dickey, was fascinated by the idea of a gravitational wave detector. We had long discussions of how you'd build one. He never did, but Ray Weiss visited Bob Dickey's group for a year, went back to MIT, and through brilliant effort, pioneered the technology of pushing this idea further and actually building the LIGO gravitational wave detector. I never had a strong opinion on whether that detector would ever detect anything. It's interesting that among astronomers, there was a considerable annoyance about the fact that LIGO is laser interferometer gravity wave observatory. Calling it an observatory was a total red flag for astronomers. You want to observe something? Give us an optical telescope. Great skepticism about whether that observatory would ever detect anything. The National Science Foundation somehow had the courage to continue funding that operation until finally it succeeded. Now that it's succeeded, gravitational wave detections, as the instrument has continually improved, are getting more and more common. It's opened up a whole new branch of astronomy, detection of gravitational wave events rather than light, X-rays, infrared radiation. And it's going to be, there's a new astronomy out there waiting to be explored.
Now, was there someone else you wanted to ask the
Nope.
question? That was it? Okay.
Professional career.
Just if it's really quick, I'm supposed to stop us now. So,
It's a quick, kind of a strange question. At the beginning of the universe, just before inflation really takes hold, the universe, like we're told, may or may not have an edge. I was thinking, it's kind of puzzling to me, wouldn't it logically be impossible for it not to have an edge? Because we're told, like, say, at 10 to the minus 46 or whatever, the universe is a certain size. And if it's a certain size, like, say, the size of a basketball, there has to be an edge between something and nothing.
Yes, you're right logically. But again, this is a problem with careless use of language. When people say the universe was the size of a basketball or a dime or an atom, they don't really mean it, because the universe doesn't have a size that we know. We see no edge to the universe. It may have an edge, but how far away? So we don't know how big the universe was back then. All we can say is we know how big the universe one can see is. It was tiny then, the part of the universe that could be observed. The part of the universe that can be observed has been growing as light has time to travel further. That's all we can say. We don't. As I said, if there's an edge, it's way out beyond our ability to observe. And so the notion of a size is really meaningless. The notion of an observable size is meaningful. How far out can you see? That's what's been increasing. how far you can see.
Okay, so let's, these are big ideas, and they're hard to wrap our minds around, right? So we can have lots of discussions later, and I noticed that actually there are refreshments over there where they can be debated over the refreshments. But before we do that, I first want to thank Jim for this. Well, he did such a fantastic job at answering questions. He was put on the spot by all of you. And he gave us a very entertaining lecture, so thank you very much. And now I'd like to introduce the President and Vice Chancellor of the University. So this is Dr. Michael Benarosh.
Thank you so much, Dr. English, and I wanted to thank Dean Brian Mark and the Faculty of Science for hosting this. And I want to say it's brave of you, the last question, to even mention inflation these days. And I wanted to thank Dr. Peebles for a really engaging presentation and for presenting what I know are really complex ideas in a way that we could almost wrap our heads around. It really is such an honor to have such an esteemed alumni such as yourself return and to speak today to all of us. So on behalf of the University of Manitoba, thank you and welcome to Winnipeg. And as a token of our appreciation, on behalf of your alma mater, I'd like to present you with a limited edition book created by our own Dr. Professor Erwin Hubner, who's sitting right here. Do you want to just wave to everybody? Thank you. He's Professor Emeritus from the Department of Biological Sciences, and he's now currently an artist in residence with the U of M School of Art. He told me that he started this as a one-year gig, did you say 5 years ago or 6 years ago? And they continued to renew him. So obviously having an impact on our students. And so this is a book that he has created. There's only 4 in existence, and it's printed using archival pigment ink. And we think it's fitting to give this rare and wonderful book to such a rare and wonderful mind. And the book is playfully titled Peep Show, and it showcases marvels of micro and macroscopic worlds. It demonstrates, as Isaac Asimov said, that there is an art to science and a science to art. Dr. Hubner's striking images fill viewers with a sense of wonderment, I believe, much like your research and your talk today has filled us. So on behalf of the University of Manitoba and the Faculty of Sciences, I present you this book. I want to thank everybody for attending. I hope you're a little bit more curious now about physics and cosmology after that talk. There are refreshments, and we can continue our discussions with some refreshments. So thank you again, Dr. Peebles.